I was really interested in reading Kafka because people are talking about it a lot in like YouTube, as well as people that I follow on LinkedIn, and then even in Tarka. So, and I had basically no idea what Kafka does, and that got me curious to know, what is this whole Kafka thing about. So, there was this post made by one of the I don't know, influencers of sorts, about all the 10 papers that you should read in 2024. And I started like that was I started January with one, and then I think in February I read the Kafka paper. So yeah, I mean, my goal for this year was to read like 15 research papers at least. And yeah, by the end of this call, if you guys know any interesting research papers, I'll be more than happy. We can discuss those. So let's kind of start with the Kafka paper, right? So uh, basically, this is like a compilation of whatever I've learned after reading the paper. And yeah, let's get started, right? So a few things before we start. I definitely am not a Kafka expert, so if you ask me anything related to like implementation or anything like that, I probably won't be able to answer. And this I am trying to I'm trying to communicate what I have learned. So if you have any point of information, or if you have any conflicting view with what is on the screen, please feel free to pitch in, and then we can learn together. That is that. And the second thing is, so this paper was really, I think, was published in like 2012 or 2011, I guess. So it's good, like it's been a decade. So definitely things have changed since the paper was published. So some information you might find, I, I some things might be contradictory, or some things might have changed in the recent implementation. But I think the core idea and the core fundamental design decisions that they have taken, I think that still remain. So yeah, so with those two things out of the way, I'd like to talk about the agenda, what we want to cover. So we'll take a look at what is Kafka and what problem does it solve, or at least what problem was it designed to solve. And then we'll have interesting design decisions that are taken in Kafka, and basically how does Kafka store messages. So these two things, right, the design decisions and the storing of messages in Kafka, will touch upon the core of the whole uh, uh, the Kafka system, the messaging system, right? So yeah, so let's start with what is Kafka. So the paper describes Kafka as a distributed messaging system, right? And the reason why the paper describes that Kafka was created was back in 2010, 2011, right? There was a lot of focus on personalization, right? Right now, if you look at your YouTube feed, if you look at your Instagram feed, your news, any of those things they are highly personalized to your liking, right? It kind of creates an echo chamber, but yeah, that's what the whole thing was back then. That how can we get more eyeballs? We can make it more engaging to people, and by showing them content that they like, right? So it was all personalization that was happening across all the social media websites. And Kafka was made by people who worked at LinkedIn, which is another like a social media website, right? So the problem that they tried to solve with this is that there is a lot of information that is generated by a user. uh, I think someone is trying to chime. Okay, so I'll continue. So yeah, so there is a lot of information that is generated by user when someone is on a website, right? If someone clicks on a link, right? If you click on a video, if you hover over a thumbnail for more than say 10 seconds, right? Where is your pointer going, right? What you know, which kind of videos do you like, and all of these things. So all of this data is generated, and this is then processed, and then the personalization happens. So Kafka in all of this system, right, the piece where it fits in is where collecting that information and then dumping it into a system which then processes and then generates those personalized recommendations and like analytics and all of those things, right? So it's mainly a bus. It's mainly for taking information from one part and then putting it into another information system, which then processes and then produces an output. So that was the uh, that was the idea behind Kafka, and people describe Kafka like a messaging system or a queue system, right? All of these are correct to a certain extent, and we'll see how they are correct, right? But generally, there are three major things or components in the system. There is a producer, consumer, and a broker. And this might seem familiar with someone who knows like the pub sub model, right? Someone who has worked with MQTT protocol. It has a subscriber, a publisher, and then a broker in between. So but it is different, and we'll get to know how later. So a producer is someone, but I think the roles are pretty much the same. A producer produces a message, consumer consumes a message, and broker is someone that manages and stores these messages, right? So very simple, three parts of the system which are very core to it. There is one more thing, topic, where a producer publishes a message to a particular topic, and then a consumer is subscribed to a particular topic. So whatever topic there is, whatever the consumer is subscribed to a particular topic, only those messages it will receive. Whatever producer, uh, whenever a producer publishes a message to that particular topic. So I think I missed that mentioning here, and I think that is also true with like an MQTT protocol. So this is like an very high level overview of what Kafka is and the three major components of the system. Now I think. I talked briefly on what problem does it solve, right? To put it succinctly, it is basically efficient and durable log aggregation. So is it that there were no other solutions for this before Kafka? No, there were. I think there was one created by Facebook called Facebook Scribe. It compares itself a lot with IBM WebSphere MQ. I'm not sure. Like I haven't really use that. So, but it compares itself with that. And the problem that uh, all of these existing systems had is that they had very rich delivery guarantees, which means that once you publish a message to a broker, then it goes to the consumer. It goes to the consumer, and it is made sure that uh, it reaches the consumer. So there is a bit of overhead there. It makes sure uh, there is a guarantee that it's going to reach. But in case of log aggregation, right? So suppose in like 10,000 messages which are talking about the user clicked on this, the user clicked on that, right? If you lose one message here and there, it's not gonna really affect the recommendation algorithm that much, right? It's just like if you lose one or two messages here and there, that's fine, right? So that was one where it deviated from the existing system, or that's what the requirement was. The second thing was the primary design constraint for Kafka is throughput. It needs that a high volume of high value of throughput, right? It pushes out messages as fast as possible. So that was one. It offers distributed support. Many existing solutions didn't offer distributed support back then. I don't know if they do today, but Kafka was built to offer distributed support. And the performance doesn't degrade with large number of messages. So as I said, right, a user who is on a website can generate in just one interaction, maybe a few hundred megabytes of data, and multiply that with LinkedIn scale, which is like gigabytes and petabytes of data, right? So there is a very high possibility that your analytical system or whatever uses that data to create these recommendations might not happen in real time, they might be offline, meaning when you do something, it gets when you do any interaction, the message gets logged into Kafka and then it pushes it to the system, right? So this happens in real time, but it might also happen that it sits in Kafka for a very long time, right? It sits in Kafka, and then maybe it's a periodical job that maybe after 10 hours or 15 hours, all of those messages get offloaded to that system, and then the system processes all of those events, right? So the existing solutions were not able to perform with high level of with large number of messages. The performance used to degrade. So that was another issue that Kafka tries to solve, right? Uh, so yeah, I mean, let's move on to like the design decisions in Kafka. So this is a very interesting one. So what happens in like what happens in our typical PubSub kind of model is that once a producer produces a message, it gets published to a broker at a topic, and then the broker pushes it down to the consumer, right? So the problem that might happen here is that, in case where there are a ton of logs or ton of these messages created, your consumer might get flooded with a ton of messages, which it is not able to process. And you also have to understand that the consumers are not always having the same computing power, meaning a consumer can have like 2 gig machine, another consumer can have like a 32 gig RAM, another consumer can have like a 1 gig RAM. So there is heterogeneity in the specification of a consumer, right? In the system specs of a consumer. So to counter this problem, sorry, did anyone want to say anything? Okay, cool. So to counter this problem, there is this pull-based approach that Kafka employs. What it basically means is that a producer produces a problem. Sorry, producer produces a message, gets published to a broker at a particular in a topic, and we'll talk about like what is inside of a topic as well in the later slide. But yeah, so it gets published to a topic, and then in a pull-based approach, the consumer makes a kind of a pull request of sorts. So it requests, I need messages of these many size, or I can consume these many bytes. Send me these many bytes of information. So what happens with this is that the consumer is in control of how much it can consume at a particular point in time, right? So that gives huge advantage to a consumer to decide when and how it wants to consume those messages. Also, there is no information stored at a broker that how many messages which consumer has consumed. So for example, if a broker goes down, right? So when it restarts, it doesn't really have to care about which consumer has consumed how much. It can just start from it can just restart, and then the consumers can again start consuming, right? Your broker is basically stateless. It doesn't have a lot of information about consumption patterns of a consumer, right? And another cool thing about this is that they can do a rewind of sorts. So for example, we'll see that later. A consumer can say that, hey, you know what? I need a message of this offset from this offset in memory, and give me the 10 bytes. So the offset can be, which is something that it is already consumed, right? So maybe it goes back in time and it kind of rewinds back to an old offset and reconsumes those messages, right? But this is kind of an advantage that this kind of strategy offers. There is one disadvantage to this though, which is basically if your broker has no idea that how many messages have been consumed, it doesn't know which messages to delete, right? Which messages are old, if they are consumed, and they are safe to delete. So it employs kind of a time-based policy that the older messages. So it's a configurable value. So say messages that are 24 hours and old, just delete them, no problem, right? So that is one solution that they offer. And yeah, I think there are other policies as well, which someone pointed out in a LinkedIn comment, which I'm not able to recollect right now. But yeah, I'll probably post that in the chat later. But yeah, so these are the kind of this is the pull-based approach that the consumers use, right? The second design decision, which was also kind of interesting, is that uh, in most of the systems, right, whenever there is a message, you attach a message ID and then you look up that message ID, right? Whenever you want to serve it to a particular consumer. But Kafka made a decision where it doesn't have a message ID. So Kafka is an append only log kind of thing. So what that basically means is that your new message gets appended to the end of the file. It never sits in between or anywhere of that. It always gets appended to the end of the file, right? So Kafka doesn't assign a message ID to an incoming message. To get the next message, the size of a message can be added to the current offset. So that basically means is that, when I'm at zero, when I'm at the start of a file, if I need to go to the next message, I can just add 300 bytes, which is the size of the current message, and I'll get to the second message. Then I'll add 700 bytes, which is the size of the current message, and I'll get to 1,000 bytes, and so on and so forth, right? So I think so with this, what it avoids is maintaining that message ID to memory mapping, right? And with like few million messages or a few billion messages, it scales up, like the size of all of these things kind of scale up, right? So it avoids that. It makes its memory footprint a bit. I mean, it saves a bit of a memory footprint, right? Yeah. So index to address mapping system can be avoided, which is again like this is again one of the things that I found interesting in the paper. The third thing, this is a bit specific to a operating system. So it uses a sendfile API. So whenever a message goes from a broker to a consumer, so again, understand that a producer and a consumer, you don't really have control over what arc or what OS it's running, but a broker you can probably deploy it on a Linux server or somewhere, right? So you have control. So so the sendfile API is available on any Unix-like operating system, and it basically takes full advantage of the sendfile API. So on the left, what you see is when you're copying a message from when you're sending a message from a broker to a consumer, on the left-hand side is what happens when you don't use the sendfile API, right? So it copies from the disk to page to application to kernel to socket, right? So there are 4 copies and there are 2 system calls that happen here, right? And in case of the sendfile API, there are only 2 copies that happen, right? It goes from disk storage to page cache, and then page cache to socket, right? So you save some memory and you also do less number of system calls. So again, this is something that is specific to an OS, but the Kafka broker uses this for very high throughput, which you talked about in the, I think, couple of slides before. And one more thing that I remember right now is that the difference between the existing solutions and Kafka was that you are not able to bulk send messages. So for example, you're trying to send a message from from a producer to a broker. The existing systems, you are not able to batch those messages in like a group of say 1,000 messages and send it to Kafka. You send it to the broker, but Kafka allows you to do that. So that is one more advantage over the existing systems that were there when the paper was kind of published. So yeah, this is the sendfile. This is the sendfile API that it uses. There is now these are the design decisions that I found really interesting, and I tried to summarize them in my way. Yeah. So now let's take a look at how does Kafka actually store these messages, right? So it uses. So I talked about topic previously, and there is one more thing that is inside of a topic, which is a partition, right? So a partition is a topic can have multiple partitions, right? So on one particular broker, there will be topic 1 partition 1. On a different broker, there can be topic 1 partition 2, right? So that's why it is distributed. And also there is one more thing called as a log. So a partition corresponds to a log, and log is a logical as a logical entity, but physically it is saved in a form of segment files, right? So you have a bunch of segment files in a log, and again, a segment file, here it starts from 00 offset, and then it goes to, whatever the size. The size of a segment file is pretty much the same. It's around 1 gig. They try to keep the sizes of the segment file same. And inside of these segment files, right? Like I said, right? Also, the Kafka is an append log. So anytime there is a new message that gets published to, say here in this case, topic 1, partition 1, it gets appended to the nth segment file. So as you can see on the right hand side, right? Any new message published to partition is appended to the last segment file. So there is a new message of, I think, size around 1,000 bytes. So that gets appended to the end of the segment file, and this is basically how the internal structure. So log is a logical entity, whereas physically it is stored in form of segment files, right? Now the next part is and pretty much the last part of this uh, uh, is the serving of the message, right? So as I said, right, it is a pull-based approach. Now, what I mean by that is when you're serving messages, so a consumer goes to a broker, and the broker with a request of offset of 800, and then and it wants to read 3 bytes, right? So it issues a kind of a pull request to a broker with this information that it wants to start reading from offset 800, and it wants to read 3 bytes. That's what the consumer tells to the broker. So in the broker, there is a sorted list of offsets pointing to each segment file's first message, right? So as you can see here, right, there is an in-memory index where message 001, it points to the first segment, then the message, I think 10,000 points to the second, and so on and so forth, right? So the advantage here is that, so if you go with that 800 offset, right, you can pretty much traverse the index and see that, hey, this value is between this and this. So it is, for example, here it is between 0th index and the first index, right? So it now knows which segment file to pick. So it is the first segment file that it needs to pick. So it goes to that segment file, and then it is 800 offset. So it goes 800 down. So it reaches that message number 2, and then it says that, hey, 3 bytes I need to read from it. And that's how it goes, and that's how it issues that, and that's how it sends back your 800 to 803 chunk back to the consumer. Yeah, and this is basically how the messages are served. So yeah, so just to summarize the whole thing, right? So we talked about the design decisions. We talked about the pull approach that is pretty novel in Kafka. We talked about the sendfile API. We also talked about message being stored without message IDs, and basically you're using the size as an offset. Then we talked about how messages are stored. And then we talked about, logs and partitions, and it's an append-only system. And then we also talked about how messages are served. So yeah, I mean, there is a lot more to talk about in Kafka. So for example, there is a whole thing on consumer groups, right? So here we are talking about only one consumer. So what Kafka does, it combines, or it groups all of these consumers depending upon the topics that they're subscribed to. And then there is like a gossip protocol that is used in between these consumer groups, using, and all of that, and basically there is synchronization between which topic and which partition does one particular consumer in a consumer group consumes. So there is definitely a lot more to talk about, but I wanted to kind of fit in into this 30-minute talk, so that I deliver some kind of value, and also I mean, it's digestible. It's not an overload of information. I hope this is an overload of information. But yeah, I think that's pretty much all I had.